Okay, I'm back. The second homework assignment from this week was from section 4.3, and section 4.3 was all about using the derivative, finally, to figure out when a function is increasing and decreasing and where relative extrema are. Okay, so let's go. Number 13, the very first problem from this section, already quite hard. Not conceptually, but the algebra is quite hard. So here we have this function, and the function is x root 16 minus x squared. And goal of this section is identify the open intervals on which the function is increasing or decreasing. Okay, let's go. Sorry. Let's go. Well, we learned that the derivative can tell us when the function is increasing and decreasing, the sign of the derivative. And so we need to differentiate this function and figure out when the derivative is positive and when it's negative. Alright, so I will write this function in differentiation friendly form. This is going to be x times 16 minus x squared to the 1/2. And now we will differentiate it. Okay, well, we should be sort of careful about this because the chain rule and the product rule need to be used. So it's the derivative of the first, x times the second, so x 16 minus x squared to the 1/2, plus the first times the derivative of the second, so that's x. Now, what is the derivative of 16 minus x squared to the 1/2? Well, it's going to be 1/2 times 16 minus x squared to the negative 1/2, back inside for the derivative of 16 minus x squared, which is negative 2x. So let's just double check that we did that derivative correctly. Do the first and the second plus the first times the derivative of the second. Looking good. And if you want to insert another step where you kind of carefully rewrite this, so 16 minus x squared to the 1/2, the 2 and the 1/2 cancel, so that just becomes negative x squared 16 minus x squared to the negative 1/2. Okay, so this assumes you're very good at the chain rule. Okay, now I have this big mess, man, and here is where if you've been kind of following along, you will have caught on by now that there's a sort of a good way and a bad way to proceed. We need to know when this derivative is positive and negative. In order to do that, we have to simplify the derivative. And there are some good ways and bad ways to do this. The good way is to factor. And we want to factor out 16 minus x squared to the negative 1/2 because that's the lower of these two powers. And when we do that, we are left with how many 16 minus x squareds? Answer, one of them. 16 minus x squared to the negative 1/2 times 16 minus x squared to the 1 is 16 minus x squared to the 1/2. And then this is just minus x squared. So actually this is just not that hard. Okay, and so continuing to simplify, I get 16 minus x squared to the negative 1/2 times, this is going to be 16 minus 2x squared. And still I'm not really done, because I think the smooth thing to do here is to factor out a negative 2, which would make this negative 2 times x squared minus 8, if I did that correctly, all over root 16 minus x squared. Now I'm putting it down in the bottom, and even one more time I shall rewrite this as the most simplified and clear way to express this derivative is negative 2 x minus root 8, which is 2 root 2, x plus 2 root 2, all over root 16 minus x squared. Okay, and so anytime we're using differentiation to learn about a function, there's this phenomenon in which the calculus takes 30 seconds, but then the algebra takes 5 minutes or something like that. And now we're still not done. This is the derivative in its most simple form. Now it comes time to answer the question, which is, when is this function increasing and when is it decreasing? Well, for that, we need to be sort of experts on analyzing the sign of a derivative when it's positive and when it's negative. Well, this denominator is going to be always positive, so it can be ignored. But this numerator is a polynomial. And what kind of polynomial is it? Well, for this class in Pre-Calc C, we spent endless weeks getting really, really good at making sign charts for polynomials. So this is a quadratic with roots at -2 root 2 and +2 root 2, but the leading coefficient is negative, which means the end behavior is like this. So this is going to be negative, positive, negative. And I'm going to label this sign chart f prime because this is the sign chart for the derivative. And so we see, based on the theorem that we learned in the lesson, that whenever the derivative is positive, the function is increasing. Whenever the derivative is negative, the function is decreasing. And this particular function only lives inside -4 and 4. Because if you give me a number that's bigger than 4, like 5, that blows up inside that radical, -5 as well. And so actually we can say that for this problem we can say that f is decreasing on the interval from -4 to -2 root 2. F is increasing on the interval from -2 root 2 to 2 root 2. And finally f is again decreasing on the interval from 2 root 2 to 4. So incredibly powerful information. We learn about what this function is doing by taking the derivative. Okay, let's see if we can squeeze more problems on here. It's just another one. Let's go. Oh, okay, here we go. 21. I'll just do it here. What does 21 say? The directions are find the critical numbers, find the open intervals on which the function is increasing or decreasing, locate all relative extrema, etc. Okay, let's go. This function is f of x equals 2x cubed plus 3x squared minus 12x. Okay, so nice little polynomial. So the algebra should be pretty straightforward. Directions 1. Find the critical numbers. Okay, so we need to take the derivative. Let's just do that. If we take the derivative, we get 6x squared plus 6x minus 12. And here I can factor out a 6, so that's x squared plus x minus 2. So that's really like 6x plus 2x minus 1. Okay, and well, what are the critical numbers? The critical numbers are -2 and 1. So critical numbers, or critical points, some people call them, -2 and 1. And what are critical numbers? You will recall from the previous week's homework, critical numbers are places where the derivative is 0 or does not exist. And what are critical numbers? They're places where we need to look for relative extrema. If I have a relative max or a relative min, then the derivative either doesn't exist there at all, or the derivative has to be 0. And so now we have learned not just that to find the critical points, but also we've come up with a way to determine whether those critical points are relative extrema or not. Okay, so let's proceed on with the problem. That's exactly what they want us to do. Find the open intervals on which the function is decreasing. Blah, blah, blah. Okay, so basically just figure out where this function is increasing and decreasing. Well, for that we need a sign chart. So I'm making a sign chart for the derivative. I call it a sign chart, so just a labeled number line. So that's -2 and that's 1. Of course, this is just a regular quadratic with leading coefficient positive. And so this is plus minus plus. Okay, so without actually writing this down, we know, based on the theorem from the lesson, that this function is increasing because the derivative is positive. The function is increasing up until -2, and decreasing from -2 to -1, and increasing from 1 to 2. And now, we know where the relative extrema are. What's going on? Using some sort of common sense, we know that this function is getting bigger, and then it's getting smaller. And so there must be a relative max at x equals -2. And what's happening at 1? Well, my function is decreasing and then increasing again, and therefore there's a relative min at x equals 1. Okay, but that's a little bit sloppy language. If we want to justify this, now the textbook didn't exactly say justified. It just said sort of locate them. But let's just practice the justification right now. For this we need the magic sentence, and this is the whole point of this thing called the first derivative test. And test is a I think unfortunate word to use for this. It's just a theorem. It's a way of testing whether a critical number is in fact a relative max or relative min. That's why it's called a test. It's a test of the critical numbers to see if they are relative extrema. And the answer is that we do have relative extrema here because the derivative changes sign. And it's really the sign change in the derivative which enables you to know that there's a relative max or min. And so if someone asks you, like say me, to justify that there is a relative max at x equals -2, then you have to write something like this. F prime changes sign from positive to negative at x equals -2. So, by the first derivative test, f has a relative max at x equals -2. That's the sort of full explanation. Okay. Good. And we will get maybe more comfortable with this. But this is how one applies the first derivative test. Okay, and then there's also a relative min at x equals -1 because the derivative changes from negative to positive. Okay, so I'll just stop there. More. Let's. All right. This. Okay. I guess just erase everything. Okay. 28. 28 is just another one of these same problems. I think this is actually a little bit different, but same kind of deal. F of x equals x to the 2/3 minus 4. Directions are, once again, find the critical numbers, blah, 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 blah. Okay, well, we just do it, man. We take the derivative. What is the derivative of this function? The derivative of x to the 2/3 is 2/3 x to the -1/3, and that's it. Okay, so writing this derivative in in algebra-friendly form, this is going to be 2 over 3 times x to the -1/3 is just the cube root of x. And now we see that this derivative is never 0, but there are numbers for which this derivative is undefined. That's 0, right? F prime of 0 does not exist. And so 0 is a critical number. And if we look at that critical number, we're not sure exactly at this moment whether there's a relative min or max there. That's why we now perform a sign analysis on that derivative. And we have to sort of be pretty knowledgeable about functions, and we have to know that the cube root of something positive is positive and the cube root of something negative is negative. And so, indeed, if you plug a positive number in here, you're going to get something positive out of this derivative, and if you plug a negative number in, you'll get something negative. And so that means that this function does have a relative, in fact, it's a relative min, right? Because the derivative is negative, which means the function is decreasing, and then the derivative is positive. And so f has a relative min at x equals 0. And on the one hand, this is sort of no surprise, because of course there's a relative min at x equals 0. What is this function? It's just bird minus 4. We know exactly what this function looks like. It's just this x to the 2/3 function, but just moved down 4. And so it's just going to be some kind of bird minus 4. And so there's going to be a relative min there, but it's a different kind of critical number. It's one where the derivative does not exist. Okay, 2 more, 35 and 53. We'll do 35 over here. This is just more of the exact same task. but you know, with sort of a more complicated function, x squared over x squared minus 9. Okay, let's go. Well, we just jump right in, take the derivative. So I'll use the quotient rules. This is derivative of the top, 2x times the bottom minus the top times the derivative of the bottom, which is 2x. The top times the bottom minus the top times the root, yeah, all over bottom squared. And so it's x squared minus 9 squared. Okay, so that's a big mess. Let's simplify it so we can figure out what's going on. So I think I'll just distribute everything out. So that gives me 2x cubed minus 18x minus another, minus 2x cubed. Okay, so that's actually quite nice. All over x squared minus 9 squared. So really, this derivative just becomes negative 18x over x squared minus 9 squared. Okay, but the thing is, maybe we should now observe that x squared minus 9 is kind of x minus 3, x plus 3. Maybe it's nice, well, so this is really like negative 18x over x minus 3 times x plus 3, but then squared. So that's really like x minus 3 squared, x plus 3 squared. Okay, we've now put in all of this effort to finding a nice way of expressing that derivative. Now comes the task of analyzing it. What are the critical numbers for this function? Well, there are several critical numbers. I guess 3 and negative 3 and 0, right, are critical numbers. 3 and negative 3 and 0. But really, I think we should just do the sign analysis right now. And what is the sign analysis? Well, okay, depending on your personality, you either want to include all 3 of these numbers or not. Personally, I just know that x minus 3 squared is always going to be positive, because anything squared is going to be positive, and this is always going to be positive. In fact, just that entire denominator is just positive always. And so really, if I want to know the sign of this derivative, I only need to look at the sign of the numerator, and the sign of the numerator is a linear function, but it's a line changing, sorry, that should be a 0, and the leading coefficient is negative, so the end behavior is like this. So this is negative positive. So in fact, that's just the complete sign chart for the derivative here. Also, the derivative doesn't exist at 3 and negative 3. Of course, the function doesn't exist at 3 and negative 3. Okay, and what do we see therefore? We see that that f has a relative min at x equals 0, and nowhere else. In some ways, we just sort of already knew what this function looked like from pre-calc C, to be honest, because this is x squared over x minus 3, x plus 3, and if we wanted now to make a sign chart for this function, notice I always label my sign chart so we don't get confused. A sign chart for this function will look like, well, here's negative 3, here's 3, and the numerator is always positive, so now I ignore that, and I just focus on the sign of the denominator, which is quadratic, so it's plus minus plus. Which is to say, if I were to graph this function, then, okay, it's even. It's actually a pretty boring function. At 3, it's undefined. At negative 3, it's undefined. We're going to get a vertical asymptotes there. At 0, we're going to have a double root. And this function is going to be and the end behavior is going to be 1 in both directions. So I have a horizontal asymptote of y equals 1. And then the function is going to look something like, I guess, positive, then negative, and there's going to be a double root. And have I done something wrong? Oh, I did do something wrong. Sorry, that was very careless. I did this with my arms, but of course then I wrote down the wrong thing, which is that this negative 18x will be positive then negative, And so, of course, there is a relative max at 0, because the function is increasing then decreasing. Sorry about that. Okay, good thing that I decided to graph this function, so I caught my mistake. It's going to look like that, and so, of course, I expect there to be a relative max at x equals 0, because I kind of know, even just from pre-calc, that there's going to be a double root there at the origin. But otherwise, this function is negative on that interval, so it looks basically like that. Okay, good. And I'm sort of ignoring whether this function crosses this horizontal asymptote. I kind of just don't care about that right now. Good. Last problem. Then we'll be done with this section. Yeah. Okay, 53. What's going on in 53? Same thing, I think, but now there's trig involved, and it gets quite hard. F of x equals sine squared x plus sine x. Okay. Good. Directions. Consider the function on the interval 0 to 2 pi. So on the interval from 0 to 2 pi, find the open intervals on which the function is increasing or decreasing, apply the first derivative test, blah, blah. Okay, so same old, same old. Let's just do it, man. Figure out all the things. Find out where the function's increasing and decreasing, find the relative extrema. Okay, so it seems like, oh, this is just another problem, and it is. Let's take the derivative. The derivative here of sine squared is, this is really means that, don't forget, so I have to do the chain rule, and it's 2, derivative of, of something squared is 2 sine x back inside cosine x, and then the derivative of sine is cosine. Okay, that took 20 seconds to take the derivative, but now we have to find out when the derivative is positive and when it's negative. And so I need to now solve the equation, sort of, or the inequality. When is 2 sine x cosine x plus cosine x greater than 0? And this is now just a pre-calculus problem, a relatively difficult pre-calculus problem though. We did this at the sort of October, early November of pre-calc C. We did a lot of problems like this, but it's been a while. I think I did one like this in the video, so let's go. Here is, I think, the simplest method. First we factor, so we get cosine x times 2 sine x plus 1 is positive. And now we just sort of think for a second and we say, okay, this is the product of two things. When is the product of two things positive? When these are both positive or both negative. And so we need to determine when each of these is positive and when each of these is negative. And so we solve now we set up sort of two separate problems for ourselves to solve. When is cosine positive? And when is 2 sine x plus 1 positive? And this, of course, is equivalent to 2 sine x being greater than negative 1, which is to say, when is sine x greater than negative a half? And maybe I'll just do this the simple way, just in one step. So we make a circle, and now what I want to do is on this circle, shade where these are both true. So let's shade when the sign is greater than negative a half. Well, when is the sign negative a half? Down here and down here. And when is sign greater than negative a half? Well, all of this section of the circle where the y coordinate is greater than negative a half. Okay, great. Next. So I've shaded purple everywhere where this inequality is true. When is cosine greater than 0? Well, that will be true whenever the x-coordinate is greater than 0. And so that's going to be here to here. So that's all of that. And I guess these purple things should be open circles, I see. Well, it doesn't really matter. Okay. And now, this should all be familiar because we did it last semester and also in the video. I now sort of look carefully at this doubly shaded figure, and I see that, okay, when both are shaded, well, let's just start. I'm going to make now my sign chart for this, and I'm only doing this on the interval from 0 to 2 pi. So when is there a change? Well, there's a change at pi over 2. And something is happening here at 7 pi over 6. So that's 7 pi over 6. But also something is happening here at 3 pi over 2. And also something is happening here at 11 pi over 6. Okay, and now I just carefully go through and say, all right, on the interval from 0 to pi over 2, the purple is shaded and the red is shaded. Well, I shaded the purple when this was positive, and I shaded the red by convention when this is positive. And so on this interval, they're both positive, therefore their product is positive, therefore my derivative is positive on that interval from 0 to pi over 2. And from pi over 2 to 7 pi over 6, the purple is shaded, which means that this is positive, but the red is not shaded, which means that this one is negative. And so on this interval, since one is shaded and one isn't, one's positive and one's negative, so the product is negative, so the derivative is negative. From 7 pi over 6 to 3 pi over 2, neither are shaded. And since I don't shade intentionally when well, since I shade but it's positive, if neither is shaded here, it means they're both negative. And if they're both negative, their product is positive. From 3 pi over 2 to 11 pi over 6, they are, again, one is shaded and one isn't. The red one is shaded, which means that this inequality is true, but this inequality is false on that interval, so that this is positive and this is negative, the product is negative. And finally here, they're both shaded again, so their product is positive. Okay, so that's really just all the difficulty here is in the pre-cal. And so now we know that this function is increasing on this interval, then decreasing, then increasing, then decreasing, then increasing. And so where are the relative extrema? Okay, I don't feel like writing this, but here at x equals pi over 2, this function is increasing and then decreasing, so we're going to have a relative max. Here it's decreasing and then increasing, so we're going to have a relative min. Here we're going to have a relative max. Here we're going to have, and here we're going to have a relative min. Okay. Good. That was all of that homework on section 4.3. Woo!